Wait, mine's was slightly different actually.
Oh,
Oh.
was yours in this format though?
Pretty similar, yeah.
Because
No, mine was like yours. That one was
yeah,
mine.
this is the Ellie tutorial one. Yeah, this
Hmm.
one I got from textbook. This is also another one I got from textbook. I haven't solved this one. I've solved this one, so I can go through both. This one's
Okay.
nice because it also shows superposition in AC.
So fun fact, I do not know superposition, nor do I remember.
That's fine. I can explain. The concept's pretty simple.
Okay,
So,
okay.
what do you think we should start first? The Ellie tutorial or the textbook one?
Let's do the textbook one. You probably know the concepts better.
Yeah. So, also use superposition so I can explain that.
Hmm.
So, the first part that you have to do is the superposition, right? Because when you have two voltages and between them is a power source, you can relate the two voltages, right? So the rule with
Okay.
a voltage source is, of course, it's going to be this plus this amount is going to be that one. So we can make the connection that V2 is equal V1. Oh wait, no, sorry.
Isn't it V2
V1
minus
is equal.
V1? Oh,
There's you can write both ways. So
okay.
the way that I remember it being is like this. So V1 is equal V2 plus 10 phasor degree 45. You can also write that as V1 minus V2. The difference of it
Hmm.
is 10 with a
Okay.
phasor of 45. They're the same thing, right?
Okay.
The main thing that you're just focusing on is relating the two. Because once you
Hmm.
relate the two, you can just ignore everything in between. Because you know V1 is the relation between V1 and V2. You can
Hmm.
literally just put it in a black box, I guess you would say. So you don't care what's in the black box, you just care how it works, and you know how it works. So let's draw the rest of the circuit here. I'm not good at drawing,
All good. All good.
but it looks good enough. So you have your superposition here, or
Hmm.
super node here. You have V1 on this side and V2 on this side. And the second nice thing about superposition or supernodes is that you can, because you can treat it like a black box, it everything, all the laws apply to it as well, right? So Kirchhoff's current law also applies to it. So everything that goes into this super node goes out of
Hmm.
it.
Okay.
You could think of this super node sort of like a building with V1 and V2 being the entrances. Stuff can go in one entrance and out the other, but everything that goes in must come out eventually. So let me just copy the rest of the circuit here. So it's negative J3. This is J6, and this is 12 ohms.
Why do they put the values after J and not ahead of J? I don't ever get that.
I
Like,
don't understand it either. I preferred the other way.
yeah,
I'm just
like
copying.
okay.
Yeah, I don't know why they do that. It annoys me as well.
Yeah,
Because
like
I don't think the calculators allow that. Let me see. Yeah, if you put J3 into the calculator, it'll literally just refuse you. You have to do
oh,
3J. I'm just gonna do it the other way.
okay.
Because, yeah, I
Hmm.
much prefer it like that. It's the same thing. So,
Hmm.
yeah, so now we just write the directions. We can assume anyway, right? So let's just assume that the current is going in. Well, we can't assume that. It's given. And everything else is
Hmm.
going out.
Okay. Wait, what happened to the resistor though? That was in between. You
The
just ignore that.
resistor doesn't actually matter at this point because
Okay.
we relate V1 and V2 using the voltage source. We don't
Mm-hmm.
actually care about the resistor in between
Okay, fire.
because there can be literally anything between these two. But because we have this direct relationship of the voltage source, we can just ignore all of that, create this equation, put it all as a supernode.
Hmm.
Because again, the supernode, all we care about the supernode is that all the currents that go in come out.
Hmm.
So we don't actually care what's in between anymore.
Okay.
But yeah, that's a good question. I think they do that to trip you up. But yeah,
Okay.
ignore that pretty much. So yeah, whenever you see the current source separated by whenever you see two voltage points separated by a voltage source, yeah, you can just do supernode, and it'll make your life easier.
Okay.
So after this, you can set up the supernode equation, right? So you start with the currents going in. So current coming into this side is just 3 with a phasor of 0. Uh, because that's the
Yeah.
current coming in.
Mhm.
And then the currents coming out will always be voltage divided by the impedance, Z, or R, if you want to remember it like it's DC.
Mhm.
So the voltage difference, we're going to assume this is our ground,
Mhm.
is V1 minus 0, because that's our ground, divided by negative 3J, plus,
Mhm.
and this one's coming out from V2 to our ground, so that's V2 minus our ground, divided by the impedance, 6J, plus, and again, V2 going to ground, that's V2 minus 0, divided by 12 ohms. And so now we can simplify this. We can get rid of the zeros, obviously.
Okay. Yeah.
And we can also get rid of this phasor domain, because of 3 with the phase of 0, it's just 3, right?
Okay.
If you draw out it, that
Mhm.
just means it's entirely real and there's no imaginary part. So that's just 3.
Okay. And then is this where they like whip out the system of equations?
Usually you would, but you can just substitute here, because we have this relationship
Uh,
between V1 and V2. So to get rid of we can get rid of V1 here, because we just want as few variables as possible.
mhm.
So we can do, instead, we can rewrite using this equation here. V1 is equal V2 plus 10 with a phase of 45. So that's V2 plus 10 with a phase of 45. Divide by 3J. I don't think they will throw many system of equations questions with us in AC. You will need to be able to, up to like 3 by 3.
Isn't yeah, isn't that
But
like Cramer's law?
yeah, because you have to use Cramer's law, it takes a lot longer. They don't they have limited time to test you on, right? So
Okay, okay.
study it, but you
Mhm.
probably won't see as much. But you probably will
Okay.
see one. It's a lot
Yeah.
of but. So you'll eventually get 3 over 1 over 3j v2. Isolate the v2, so you get plus 10 with phasor of 45 degrees over negative 3j plus 1 over 6j v2 plus 1 over 12 v2. And
Mhm.
now you can
Just
pull
solve for
out the
V2.
v2s. Yeah, you can solve for v2 at this point, right? This is just algebra. So we move the constants to one side, so that's 3 minus 10 with a phasor of 45 over negative 3j is equal to, pull out v2, so you get v2 times 1 over negative 3j plus 1 over 6j plus 1 over 12. Right, it's pulling out the v2.
Mhm. Yeah.
So you take this, you divide it out. I'm too lazy to rewrite that, so I'm just going to copy and move it.
Oh my god, that's nice.
And you get this. You will get really bad equations like this. Honestly, don't simplify it further, because you could just shit it into your calculator.
Yeah.
Um, I would show this, but I don't know how to do complex operations like on the computer. If you have
Oh,
the
okay, that's
yeah,
fair.
if you have the
Yeah.
Casio 991 ES, there's a complex
Yeah,
node. Yeah,
Casio gang. Casio
Casio
gang. No
the
Sharp.
the Casio calculator is just objectively better. I'm sorry,
Yeah.
Sharp users.
Fine.
The only annoying part you have to keep out for, first of all, make sure your calculator is in degrees, right? Because if it's in radians,
Mhm.
these phase angles will be assumed to be in radians. And
Yeah.
second of all, I don't know why, but when it is in complex mode, usually you can't go back and change after you've calculated it. So make sure your formula is right, putting into a calculator, or else if
Mhm.
it's wrong, you have to go retype the entire thing. I think that's a limitation of the system. I'm not sure what's up with that. Point is,
Oh, damn.
yeah. So you put that in the calculator, you get that V2 is equal to 31.4 with a phasor of negative 87.1 degrees. Dot 2. Is that
Mhm.
right? Because let me see.
Yeah.
Yeah, 31.41 with phasor of negative 87.18 degrees. Yeah, so
Mhm.
you got your V2, and now you can use your original relation between V1 and V2 to find V1.
Mhm.
So bring that formula down.
Yeah.
Just
Plug in the value.
yeah, just plug in the values. That's it.
And shit into your
So
calculator.
that's yeah, shit into your calculator. Phasor with a angle of 45. You get 25.8 with a phasor of negative 70.5 degrees. So
Mhm.
that's a good example of nodal analysis with a superposition that you don't actually need to do a system of equations with. And again, most things are like that. Same thing here. So this is the one that we got in our ELE tutorial.
Yeah.
We This is the entire thing, and we're asked to find VO as in time domain.
Yeah. So the four different ways of representing it are like complex numbers. Are polar, rectangular, time domain, and phasor domain?
Yes. So there's polar. Yeah. So polar is something like 20 with a phase angle of 30 degrees. You have
Mm.
rectangular, which is just the real plus the imaginary component times I,
Mhm.
or in this case j.
Yeah.
And then you have time domain, which is uh like VO is equal to what's that? The peak to peak. So it's a voltage peak to peak
Mhm.
of cosine. Uh oh lord, I'm blanking. There you go. Of
Plus
omega
phi.
t
Yeah.
plus phi. Yeah. And polar is written peak to peak times phi.
Mhm.
So so first of all, the first thing you do when you're calculating this is obviously change it to polar form. So let's take this. I don't know why, but the standard is that you put the impedances as rectangular and you put the sources as polar. I think it's just easier like that.
Oh. Okay.
So 20 cosine 2t plus 10. So that 20 is our VP to P, peak to peak.
Mhm.
Actually, no. Oh, this is our amplitude, actually.
Yeah. 20 is the amplitude.
Yeah, sorry. Not peak to peak, that's amplitude. That's our VA. We can remove the cosine, and then we just take our phi out. So
Mhm.
with angle phi, so that is 20 with a phasor domain of 10 degrees.
Wait, don't you have to turn into sine or something for phasor? So you have to have plus or minus 90?
The other
Forgot
way
which one.
around, you have to turn sine into cosine. So if you had 20 sine 2t plus 10, the
Mhm.
formula you have to turn that into cosine by doing 20 cosine 2t plus 10 degrees minus 90 degrees.
So cos is always phasor.
Yeah, cos is a
Okay,
phasor.
okay.
We start at 1. I don't know why exactly cos is, but that's just how it is. I think you would have to graph it out to see.
Okay.
But yeah, so
Mhm.
20 cos 2t plus 10 degrees turns into 20 with a phasor domain of 10. And now we need to turn this capacitor into rectangular form. So the formula with capacitors is that the impedance for a capacitor is equal to 1 over J omega capacitance. Just as a reminder, the inductor formula is the inverse of it. So it's JW
Mhm.
inductance. We don't have an inductor here, so
Yeah.
just a capacitor. So Z of the capacitor is equal to 1 over J, the omega is this one, 2 here. So that's 2
Mhm.
with a capacitance of 0.5 microfarads. And so those two cancel out, you get negative J. So one of the identities is that 1 over J is equal negative J.
Okay.
You can put that into your calculator as well. You don't actually need to remember that. If you put 1 over negative or 1 over I in your calculator, it will actually just spit out negative I. So,
Okay, that's fine.
yeah. So we rewrite this as negative J. So now we have our system changed to phasor domain. And now we can calculate. So, to find the voltage variance here, we need to find the voltage here. Because we're going to assume that this is our ground. The bottom is always ground. So therefore, this VO is just equal V2. But we can't really find V2. It's messy, so we'll find V1 first. And V1 we could solve using nodal analysis. So let's just assume the directions. We have IX coming in. We have this 2IX dependent circuit coming up. And then everything comes out this way. So let's start with the in. It's always from -2. So 0, it comes from ground up through the. Did I copy this wrong?
No, that should be right.
Let me see, because I do have a picture of the. Oh, I did not copy it right. Oopsie.
Oh, what did you? Oh, the
I
capacitor's
forgot.
over there.
I forgot inductor. There's an inductor.
Oh, shoot, you're
Yeah,
right.
because otherwise this circuit is actually unsolvable.
Oh,
Oopsies.
not bad.
So sorry about that. Okay, so we do have the inductor here. So the Z inductor is equal to JWC or JWL. I didn't write it, 2 henries. Yes. So that is J2 2 or 4J. So this inductor here is 4J. Let me write that there.
Mhm.
4J. There's the current going over there. So again, nodal analysis properly this time. So
Mhm.
always remember you do from -2. So it comes from ground here, right? This entire part here is ground. It goes up through the 0. It goes up through the voltage source. So that's +20 with a phasor of 10 degrees. Comes out the positive side, it's going to be positive. Comes out negative side, it's going to be negative. And then it ends at voltage 1. So this is the from, and that's a 2. You always write like that. So let's move that down so I can have some more room. Let me just move this because you already know it. So you
Wait.
divide that by the impedance, in this case 4J, plus there's another source coming up. So that is 2 times IX. Now what's IX? Actually, we just wrote the formula for it, right? This entire thing is IX because we are doing current law.
Oh, is that the
Kirchhoff's
current law
current law.
from like IX to V1?
Yeah,
Like,
so
okay.
yeah, the nodal analysis is Kirchhoff's current law. So you are
Mhm.
just doing. So what this entire formula is the current, because current is voltage divided by impedance or resistance.
Mhm.
So the current flowing through here is actually just this. So we can copy this entire formula, right?
Mm-hmm.
Ix is just 0 plus 20, impedance of 10 degrees, minus V1, minus 4J. And that's 2 times that, so we have the 2 in front. So we have that. And then so that's all of the currents going in. Now we do currents going out. Let's ignore V2 for now, because we don't know V2 at all. And we can't really solve for it yet. Just focus on V1.
Mm-hmm.
And so this way going here, it comes from V1, ends at ground. So V1 minus 0, and the impedance is the sum of the impedances. So that's 10 minus J. So that's our nodal analysis formula for V1, just
Okay.
V1. Yeah.
Okay, gotcha.
The nice part, yeah, unfortunately we do have the V1 here, so we need to go rearrange all of this stuff. We can remove the zeros, obviously. So that becomes 20 with a phasor of 10 degrees over 4J minus 1 over 4J, V1, plus 2 times 20 with a phasor of 10 degrees over 4J, minus 2 times 1 over 4J, V1. This is just expanding, right? We can remove that 0 is equal to 1 over 10 minus J, V1.
Okay.
And yeah, so move all the constants to one side, move all the V1s to the other side, you know how it is. So that's going to be negative 1 over 4J, V1, minus 2, 1 over 4J, V1, minus 1 over 10 minus J, V1, just moving that to the other side, is equal to, now move the two constants here, and we get negative 3, 20 to the phasor of 10 degrees, over 4J. These two are the same, so we can just add them up. So that's 2, that's 1 at the front, 3.
Yeah. And you just plug that onto the calculator.
Yeah, so you isolate, you get V1 is equal to negative 3, 20 with a phasor domain of 10 over 4J over negative 1 over 4J minus 2 over 4J minus 1 over 10J minus J. Sorry. Not, yeah. 10 minus J, not 10J. And yeah, like you said, you just plug this entire formula into the calculator. I wouldn't recommend simplifying it further because you're just opening yourself up to messing up.
Mm-hmm.
So 20 with a phasor domain of 10 over 4J, or 4I,
Mm-hmm.
and then at the bottom here, you have negative 1 over I. Oh, that's 4I. Minus. Did I? Oh, no, I did that right. Okay. Minus 2 over 4I. Minus 1 over 10 minus I. You do that. Calculator slowly takes time. And you get. Alright, let's move that to the left here. You get that this entire thing is equal to 20.08 with a phasor domain of 2.38 degrees. Now that's just V1, so we're not. Oh, sorry, I can't round properly. That is 09. That's just V1. So we aren't actually done this question yet because it's asking for VO between the two, and don't forget in time domain, not as a phasor domain.
Mm-hmm.
So let's copy the circuit down because it's too far up.
Hello.
Well, I was joining now.
Yeah.
TMU time. What can I say?
TMU time. So we can now use V1 to find V2, right? And this is pretty similar. So to find How did I do this last I checked? So you can simplify this to be, so you have V1 on this corner. You have the capacitance, the capacitor of negative J. You have V2 here, and then you have resistor, and then you have ground. And actually, there's multiple ways to solve this, but you can actually just do a nodal analysis again, right? So you know that current comes in here, current comes out. So the current coming in it's always from -2 divided by the impedance, so that's V1 minus V2 over negative J is equal to, again, from -2, so that's V2 minus 0 over the resistance of 10 ohms.
Quick question.
Yeah?
How do we solve these equations quicker?
How do you solve the what?
How do you solve these complex equations quickly?
Use your calculator. Do you know what calculator you have?
Yeah, I have a 991 CW.
CW?
Yeah,
FX991CW, like that?
yeah,
Oh. Okay, yeah, so that has complex in it. You could see there. I don't
yeah,
know how you would set that up because I have the 991ES, but you can
Yeah.
definitely search for the manual. You will find the manual telling you how to put in complex equations. Once you have
yeah.
that done, you could just put in the equation.
The thing is, we'll have to substitute, we'll have to reduce everything into one equation, right? We can't solve simultaneous equations, if I'm not wrong.
We will have to using Cramer's rule. So,
L- Okay, if we were given a hypothetical case, we were given 5 unknowns. There's no way we can do Cramer's rule, right? Like we can, but
five
that's
unknowns.
gonna
Yeah,
take.
no, not 5 unknowns. I think the absolute maximum that they will get to is 3 unknowns. Because 3, you can use a very simple formula to solve 2x2 determinants and 3x3 determinants.
Yeah,
Yeah,
yeah.
I can go over, but I still have my notes from linear algebra. 3x3. Let's see if I have that written down.
Then what's the software you're using?
This is logsec. I use it to write down all of my notes. But yeah, I still have my linear algebra notes. I can post them in the server. They're still pinned in the linear algebra chat, I think. But
I see.
yeah, so there's some really simple formulas. That's just multiplication and addition to find a 3x3 matrix. And obviously you can find the 2x2 matrix doing
Just cross
where is it?
multiplying the diagonal elements and subtracting them.
Yeah, I forgot where I put it, but if you have a matrix like that, the determinant is
AD.
just AD minus BC.
Okay. Thanks,
Yeah.
man.
So that's a Cramer. You need to know the determinants for the Cramer's rule. But let me just finish up this question first, because we're at the home stretch here. So if you have so yeah, you can do nodal analysis again on just this singular line. Oh, he's gone. That's all you needed to know. So you do V1 divided by minus J minus V2 divided by minus J is equal to V2, or 1 over 10 ohm V2. Let me just properly remove that out. So that's 1 over
Combine the
negative
V.
J V2. You can remove that 0. Yeah, so you're just expanding this. And again, it's same thing over and over. You have V1 minus negative J. You know V1, so you treat that as your constant. Is equal to plus 1 over negative J V2 plus 1 over 10 ohm V2. Factor that out, you get V1 over negative J divided by 1 over negative J plus 1 over 10. Again, you're going to have divisions over divisions over divisions. You can simplify them. Don't bother. You might just make a mistake. It's not worth it. So you put in, we know V1, so that's 20.09 with a phasor domain of 2.38 divided by negative I. All of that divided by 1 over negative I plus 1 over 10. All right, yeah. So you get a voltage of 19.99. So nearly identical voltage actually. But you will notice it does drop by a very slight amount depending on the capacitance with a phasor domain of 8.09 degrees. So this is your phasor answer for V2. And as we wrote here, V2 is equal to V0 because it's just V2 minus 0. It's V2. So this is our phasor domain answer. However, the question asks us to put it in time domain. So again, we have to
add 90
undo.
degrees.
No. So we have to just undo polar to time. So you do have to add 90 degrees if you write it in sine form. But we're just not going to because sine form is annoying. So you get 19.99. Oops. Almost wrote sine there. Cosine. Now the angular frequency is going to be the same in an AC circuit. Everywhere along the AC circuit, if all of your sources have the same angular frequency, everywhere in your circuit's going to have the same angular frequency. So that's going to be 2t, and then plus your phi. So that's 8.09 degrees. So your V0 as a function of time is going to be that. There's your answer.
I'm confused. I thought you said sine was time domain, and this is phasor. Cos is phasor.
Cos is time. Oh, writing time domain is just how you write it. It's the same thing. You're expressing the same thing, but you're just writing it differently. So time domain, the proper or the best way to write time domain is the amplitude times cosine of angular frequency times time plus phi.
So therefore, turning it into sine would be a phasor domain.
Sine and cosine are both time domains, so you can.
Okay.
Yeah. So if you have some amplitude with, or would be R with a phasor degree. So this is phasor. In time, you can write it as two ways. You can either write it as R. Sorry, I'll answer that question in a second. Let me just finish this up real quickly. R times cosine of omega t plus phi, or you can write it as R sine of omega t plus phi, I believe plus 90. Let me see because
Wait, no, I think sine should be minus 90. I believe.
Let's see, because I know the formula. If you have sine, it's a sine with some phi. It's R phi minus 90 degrees. So, yeah, I think that would be plus 90. Yeah, because if you have sine 10, you would get your phase. So say if you had a sine of 10 degrees. So that's just omega t plus 10 degrees. In phasor, that would be negative 80 degrees. So turning it back, you would have to add 90. Yeah, so these are co-angles, by the way. You can find them on your trig identity sheets. But yeah, just focus on cos. If you see a sine, your first thought should be to convert it to cos. Because sine is just off by 90 degrees. You're asking to forget and fuck it up. Okay, so the fish asked, what would you say is the best method to learn or practice like this? I would say like textbook lecture recordings, YouTube videos. Honestly, I'll be perfectly honest with you. I think they overcomplicated the lectures. What I would do is look over what they teach in the lecture. Like, look over the concepts they teach in the lecture, so you know what to study. Look to YouTube videos to see how they're done, and then look to your textbook to find problems to solve. You need to have all three, because if you don't know what they're teaching in class, you're gonna go to the exam not knowing some stuff. The textbook's not good at explaining either, so you will have trouble doing the problems if you don't know how to do them, obviously. But if you just do the YouTube videos, you're not going to have the experience. I did that for the midterm. I did the YouTube videos. I saw all the theory. I studied all the theory. I did none of the questions in the textbook. That really fucked me over, because you actually do the questions in the textbook and you go, "Oh, that's something I haven't seen before. I haven't expected." And now I can figure it out. I can go back to YouTube videos, review, all that fun stuff. So, yeah, do all three. Lecture to figure out what to study. So that's the what. The YouTube is the how, and the and textbook is the grinding. That's where you grind your ass off doing all the practice problems, so you know everything that will be in the book. Let me try and find it. There's a great electrical series on YouTube. Electrical engineering. Here it is. This guy, Michael Van Beezen. I'll put a link in the chat. I think I already did a while back, but I'll do it again. This guy goes over the examples. He basically does what I'm doing right now. He goes through the problem. He shows how he does all the calculations. Very nice. The only downside is that his circuits tend to be a lot simpler than what we do in class. So keep that in mind. He shows you how to do it, but he will not show you the harder questions. So you need to practice, you need to study, you need to actually go there and do it. Did I do this question? Oh, I did. Let me see, because I'm thinking of doing a okay, yeah, so that pretty much answers your question, I hope. I'm thinking of doing one with Cramer's rule involved, because I know that people don't really know how to do Cramer's rule. This question from textbook has Cramer's rule, so I'm going to try to do it. So, this one, we are going to do nodal analysis again. Actually, yeah, nodal analysis. I think a lot of the earlier ones just do nodal analysis, but do keep in mind the concepts for DC basically apply nearly identically to AC. Both nodal analysis, mesh analysis, superposition, Thevenin, all of it that you've done in DC is pretty much identical to AC. The only difference is using complex numbers, really, and having to deal with them. And you can't reduce complex numbers in your calculator, which sucks, by the way. That's awful. But anyway, I digress. Yeah, complex numbers are not fun. I don't know who decided to put them into electrical. I don't like them.
Maybe when the electricity is imaginary.
Exactly. See, that's the thing. AC circuits use imaginary numbers. That means that by relation, AC circuits are imaginary. They're not real. It's fake, made up by the government.
To charge you for their electricity usage.
Yeah, the electrical bill, the electricity companies aren't actually doing anything. They're just making up shit. Oh, cost to get to you. They're embezzling. Anyway.
Apparently TMU, like previous like Eng faculty or something, did that. Like TMU's presidents and stuff, they did that by faking construction projects, and they started embezzling the money.
Yeah, that sounds like student council.
Yeah.
I swear to God, every single student council, university student council has some level of embezzlement going on. I heard that from my friends at Guelph. I heard that from friends in Ottawa. It's insane.
It's free money.
Free money. People who do politicking are built different, I guess. Anyway, so this problem, it's asking us to find Ix here. So find Ix here.
Mhm.
So obviously, first step, convert it to phasor domain. This is all time domain, convert to phasor. So this is 10 ohms. You don't change that. Let's convert this first to phasor. This actually doesn't have a phi at all. So phi is 0.
Yeah.
So that's 20 with a phase of 0 degrees. Or actually just straight up 20. 20. Because a phasor of 0 means no complex at all. You can confirm that, put in your calculator, anything with a degree of 0. 1 Henry, again, the impedance of an inductor is JWL. I swear that's like a company. So W is 4 here, right? From our single voltage source. So that's J 4 with 1 Henry. So that's 4J. So that's 4J here. This is 0.1 farads. Farads invented farads. So we have capacitor is equal to 1 over JWC. W is 4 again. And so that's going to be, what's 4 times 0.1? 0.4. I'm stupid. So that's 0.4J.
It's better if you write it as 2 over 5. Makes it easier.
That is true. Let me see. 1 over 0.4G. Yeah, your calculator will write that, right? So that's negative.
Negative. It should just be 2.5J, no?
Yeah, 2.5 over J.
Mm-hmm.
Let me see. I have my calculator set to polar form.
That's how it becomes negative. That makes sense. Wait,
Yeah,
you set your
move.
calculator to polar?
Yeah, I leave my calculator on polar. I think polar is just nicer to deal with, but both will work. You will get the exact same answer. You could do all of these calculations in rectangular form. You'll get the exact same answer, right? So we could actually move this J up to be negative 2.5J, right? Because you have the identity that 1 over I is equal to negative I. Again, you can put that in your calculator, confirm that. You don't actually need to remember it. But it's nice for simplification. So this is negative 2.5J. And yeah, so that's negative 2.5J. This is 2Ix still. And this is 0.5 Henrys. Same thing as above. J times
Just
4
2J.
times 0.5, so that's 2J. And so we've converted the circuit from time domain to phasor domain. That's all you do. And now you can apply nodal analysis just as you would DC circuit, right? So let's assemble the two formulas. Let's assume some directions for currents. So that's going to go this way. That's going to go that way, obviously. This current's going to go up that way. That's going to come out that way, and let's say that this is going this way. Again, the assumptions don't matter at all. They're just a direction that we say is the positive direction. If we get a negative direction, we just know that the current is actually flowing the other way. So, let's start with V1, or node 1. So, as always, you start with the currents flowing in from -2. So, this is our ground here. So, this is going to be 0, starting from ground. It goes up the voltage source to gain 20 volts. Comes out positive, it's positive. And then it ends at V1, so minus V1. That's your from, that's your to. You divide that by the impedance, 10 ohms. The second part coming in is this one. So this is going to be from V2. So plus V2. It ends at V1, so minus V1 from V2 to V1 divided by the impedance, 4J. And then is equal to the output. And again, we do the exact same thing. So from V1, and it heads to ground. So it's V1 minus 0 is equal negative 2.5 J. By the way, I'm just writing this 0 to be very clear why I'm writing 0. You don't need to at all. So that's V1. That's node 1. Let's do node 2. Actually, let's simplify node 1 first to the best of our abilities. You can do either way. So 20 divided by 10, that's 2 minus 1 over 10 V1 plus 1 over 4J V2 minus 1 over 4J V1 is equal to... Actually, let's pull it to the other side. So we're going to get negative... Actually, let's not confuse ourselves. Try not to skip steps in when you're actually doing them, because it's very easy to forget a minus sign or something. So you're going to get 1 over negative 2.5 J V1. You can ignore the 0 there. So now we move all of the voltages to one side, and we put the constants on the other. So that's going to be negative 2 on this side, and we're going to get negative 1 over 10 V1 plus 1 over 4J V2 minus 1 over 4J V1 minus 1 over negative 2.5 J V1. Again, you could simplify this. I wouldn't recommend it because it's going to be the same when you put in your calculator. So you get V1 negative 1 over 10. So we collect that one. Let's collect this one. So that's negative 1 over 4J. Collect this one. So that's minus 1 over negative 2.5J. Oh, don't write the V1. And then we collect the V2. So that's just V2 1 over 4J. Is equal to negative 2. So that's our first node. That's the first system of equation for our node. The second system of equation, I'm going to copy this entire circuit because it's too far up. I'll go delete it later. So second V2, again, start with the ones coming in. So that is 0. So that's 0. And then, actually, this isn't voltage divided by impedance because we actually just know the current itself. The current here is 2Ix. And now we come out. So it's equal to V, again, from minus 2. So that's V2 minus V1 over 4J plus from minus 2. So that heads to ground. So it's V2 minus 0 over 2J. Now we need to expand out this Ix. This Ix is the same exact current that's flowing through here. The current is equal voltage over impedance. Where did we do that before? We did that up here. So this part here is this here. So the voltage is V1 minus 0 over the impedance, negative 2.5 J. So that's 2 of that is equal to all of this fun stuff. Actually, let's expand it out. So that's 1 over 4J V2 minus 1 over 4J V1 plus 1 over 2J V2. Remove 0. Remove that 0. So again, we can expand this out even further. That's 2V1. Actually, 2 over negative 2.5J V1. And now let's move that to the other side. So that's all of this stuff comes down here. Move that to the other side, minus it. We have 0 here. So now we have our two equations. Let's remove this circuit here because the same thing is above. Our first equation here is this, and second equation here is this. And now we need to put it in linear algebra form. So the determinant, or our matrice. Let's go calculate this. So this is let me move this down. Oop.
You should probably factor out the V1s and V2s in the second one.
Oh shoot!
Make it
I completely forgot that. Yeah, I don't know how I managed to forget that. Let's factor that out. Good catch, because I completely forgot for some reason. Actually, it's put on the left side. So that's so V1. So that's V1 negative 1 over 4j. Collect this one. So that's minus 2 divided by negative 2.5j. And now collect the V2s. So that's plus V2 1 over 4j plus 1 over 2j. You don't have to draw these circles, but I've found that sometimes I accidentally factor out more than once or forget to factor it out. I'm a blunder machine. I will get all of the theory right, and then I will fuck up the actual execution. If you find yourself you're like me, then do it like that. So we're gonna do here. This is V1. This is gonna be V2. Actually, let's make this extra wide because it's going to be a little bit cramped otherwise. Let's draw an imaginary line in between. This is our first node. This is our second node. Yeah. So if you remember linear algebra, it's V1, V2 is equal to our answer here. So this is negative 2, and this is 0, right? And then we need to calculate these numbers. So this big-ass thing here is our first. This is our first equation. This is our second. V1 goes in here. So just put that in your calculator.
Call it A.
Yeah. So, well, what you could just do to save yourself some space is just calculate. Put in your calculator. So that's minus 1 over 10 minus 1 over 4j minus 1 over 2.5j. Don't forget that big point there, because I've done that mistake before. Of course I have. I've done every mistake under the sun. So negative 2.5i. And we're going to get... Actually, I think it's going to be nicer if I write it out in rectangular format. Again, it's the exact same thing. So that's negative 0.1 minus 0.15j. And let's do the same with V2. So that's 1 over 4j. 4i. Put that into rectangular form. Oh, I'm stupid. That's just negative 0.25j. And likewise down here. So second one, we're going to do minus 1 over 4i minus 2 over negative 2.5i. The reason I think you should write out these answers is because you're going to be doing a lot of multiplication with them. So it's just easier to have them like this and not in big equations. Make sure you don't make any mistakes, obviously. 1 over 4i. It's tedious, I know. Over 1 over 2i. Put that in complex form, so that is negative 0.75i. So we have assembled our matrix. So Cramer's rule states that V1 is equal to the determinant 1 over the determinant, or delta 1 over delta, and V2 is equal to delta 2 over delta. Wait, let me just confirm with the textbook that I've gotten the right answers, because it'd be really funny if I didn't get the right answers. I did not. Uh-oh. Okay,
Wait, can you
let's...
go back down? Oh, wait, you're saying the V1 and V2 values are wrong?
The matricy values are wrong.
Oh,
Oh, no. Oh,
what did they do?
I'm looking here. So you get that 2. All right, let me try comparing here. So we start with 2 times V1 over negative 2.5J, and that's plus V1. Okay, so they assume the other way is equal V2 over J2, yeah. So 15V1 plus 15V2 is equals 0. Huh, so they got the same top answer, but they got a different bottom answer.
That is strange.
They completely removed the J. Oh, they multiplied the J out.
What the fuck?
Yeah, it's...
That is strange.
I think they multiplied the J out. How did they even do that? So... Sorry, yeah, you'll see you do a lot of this as you're reviewing the textbook. Don't give up. You're just going to end up wasting yourself the opportunity of learning. Or in other words, figuring out why the fuck you fucked up.
Mm-hmm.
So let's see. They put the equal sign on the opposite side. It's the same formula, so
Wait, this is so sad.
by
You can't put...
Yeah.
No, like, you know how there's the equation solver, right, in the calculator? You can't do that with complex numbers. Unfortunate.
Really? Oh my god.
Yeah, I tried plugging it into the equation, like the matrix tables that they gave you, right?
Oh,
It
that's
does
not...
not work with complex.
Oh yeah, the matrix tables don't work with complex numbers. That's why we learned Cramer's rule, and that's why we didn't learn it on the for the midterm, because we were expected to be able to just do our RDF using our calculators.
I see. Yeah, I guess it's just store it as variables and put it in, I guess.
All right,
Really.
let's try and redo this. See where we fucked up. So we have still this original equation. It's the same equation between the two. So let's copy this over. Is equal that. So we get that. We multiply that, and so that's 2 over negative 2.5j v1 is equal to 1 over 4j v2 minus 1 over 4j v1. You know what? It could just be that they wrote it differently. Let me see. Let me put this into a matricy solver. So that's a is equal to... Let me put in my values here. Because it could just be that they just multiplied something out. Because you know how REF works.
Yeah.
0.1 minus 0.15i negative 0.25i semicolon negative 0.55i. By the way, you can use MATLAB for this. It's very nice. So let me just show my work here.
I
You
know the
put...
use of MATLAB.
Yeah, the only downside, you can't put polar coordinates in MATLAB. They don't support that as a first party feature, so to speak. So is that right? Yes. I'm not using MATLAB. I'm using a free alternative called Octave. It's the exact same commands. So rref a Oh my fucking god. Determinant of A. You get that. Okay. Divide by 15 minus 5i. Let's see. Okay, I think I guess I got the wrong answer then. Because I'm unsure how they got that this is 11v plus 15v1 v2 is equal to 0. Let's see. I will admit I did not do these questions in advance.
All good, all good. That way we can both get it.
Oh yeah, you know what? They just times j times this entire thing.
Oh, to cancel out the J's. I
Yeah,
see.
probably. So that would be yeah, wait, sorry. Did that even work? Oh, it would. Yeah. So that just becomes 2 over negative 2.5 v1 is equal 1 over 4 4 v2 minus 1 over 4 v1 plus 1 over 2 v2. I feel like you would get the same answer either way. I'd have to check. But okay. So that becomes putting that all together. Let's move that to the other side. Oop. So putting that all together, you get v1 negative 1 over 4 minus 2 over negative 2.5 plus v2 1 over 4 plus 1 over 2 is equal to 0. And now you can calculate those coefficients as normal. So 2 over negative 2.5. So that's 0.55 v1 plus. You know, you probably will get the same answer. I'll have to double check right after this because I just want to follow the textbook to make sure that I'm not veering off the path. So that's 1 over 4 plus 1 over 2. I need to use a calculator for that. Right, and so they multiplied both sides by the lowest common denominator, so that would be... What's that? Lowest common multiple of 0.55 and 0.75? Either way, you multiply them, you get v1. Sorry. What's 11 divided by 0.55? That's 20. So we multiply both sides by 20. Yeah, so that's a textbook solution. You can simplify them. Yeah, you would get the same solution either way. So you know what? Let's not do that, and let's just stick with what we have right now, because we'll get the same answer anyway. But that is one way to sort of like simplify it in between before you do Cramer's rule. So now you do Cramer's rule, right? So the determinant, delta here, is just the it's just this stuff here. It's just a determinant of this. I'm gonna put a dotted line here so you don't confuse yourself. And then delta 1. So this is a part that most people don't sort of get caught up because it's like it's never explained for some reason. When you're doing delta 1, so the first line here, you copy over this column, the equals column, into the first item. So it's negative 2, 0. Let's put a comma there. And then when you put the rest is normal. So let me just repeat that with delta 2 just to be extra clear, right? If you have delta 2, you copy over the original matrix as usual. So that is this here. And then you replace the whatever column is here, right? The second column here with the equals part here. So you take this and you put it as the second column. You replace the second column. And you get -2, 0.
For real.
Thank you. Alright, yeah. So, Cramer's rule. That's all it is. So that's so you just find the determinant using solving 2x2 matrices, right? So that's this that's the cross this way minus the cross that way, the multiple that way. So let's put that into a calculator. If I do the calculations, I get, so delta here is 0.025 plus 0.075 J, right? Delta 1, again, so that's just these two multiplied minus these two multiplied. You could search up determinant of a 2x2, determinant of a 3x3. There's formulas for that. I'm just going to flash it on screen again. I'll put it in the description. The determinant for 3x3 matrix. If you don't want to do like the MIG way, that way I hated it, you can use this formula here. So it's the left side, or sorry, the R here, calculate here, minus L here.
Mm-hmm.
Both work. You'll get the same exact determinant, of course. So this one here, so that's -2 times -0.75 I. Let's save that as a... Okay, so that's 1.5 I, or J. You could skip this part because these two multiply to 0, right? And same here.
Mm-hmm. Yeah.
So delta 2 will just be minus these two combined. So that's minus -2 times -0.55 I. Save that as rectangular. You get -1.1 J. And now you can calculate your voltages. So voltage 1 is equal to delta 1 over delta. I believe that's a formula. That's a formula, right? Yes. So delta 1 over delta, you get, okay, 1.5 I divided by 0.025 plus 0.075 I. And you get, God willing, yes, you get the right answer. Nice. Okay. Yeah, so the textbook just unnecessarily simplified their stuff and didn't explain. So you get 18.97 with a phasor angle of 18.4 degrees. And if I look at textbook, there's your answer. Same answer. So now V2 is equal to phasor 1, or delta 1 over delta. Delta 2, sorry. Delta 2 over delta. And so you just replace the top. So that's -1.1 I. And you get 13.91 with a phasor angle of -161 degrees. Wait. 161? Oh, the 13.91 with a phasor angle of 198. Okay, yeah, so the textbook writes this answer as 13.91 with a phasor angle of 198 degrees. Those two angles are the same. If you put 198 degrees in your calculator, you'll get -161 degrees. I don't know, yeah, I don't know why they're using 198. This degree here, the stuff in the phasor domain shouldn't be above or below 180 or -180.
Yeah, that makes sense.
Because there's two angles, right? You can take it from the negative direction or the positive direction. You're supposed to take the shorter direction. I don't know why the textbook took the longer one. Anyway. So, that's how you solve a circuit, this entire circuit, nodal analysis, with two unknowns using Cramer's rule. Now, I think you could solve this using system of equations, but yeah, that's how you do it using Cramer's rule. You can simplify it; you'll get the exact same answer because you're going to end up dividing by your simplification again. You're going to get the same answer. So if you look here, they have a completely different matrix here. This bottom part is multiplied by 20. This top part is multiplied by, I think, like 100 or something. But you get the same answer at the end. So those are the three problems I really want to show off. Oh my god, it's been an hour and 20 minutes.
Hey, time flies by when you're coping hard.
Yeah, pretty much. Yeah, you need to... I was saying about grinding on textbook. You need to be able to solve these fast because you're not given a lot of time on the finals. It's insane.
Yeah, it's rough.
Again, you got 2 hours to do the final. Like if you didn't grind the textbook and you got your speed up fast, you're gonna be left behind. So time yourself while you're doing these questions, I guess, or figure out some way to do it faster. Well, I guess as you're grinding out, it gets so easy that you start skipping steps. You do it faster, you write faster, you get the ideas faster. So yeah, here's Supernode. These are all nodal analysis, but we use supernodes. This was time domain. And this here was Cramer's.
Oh yeah,
Also-
you're using the 6th edition textbook, right?
Yeah.
Because Fish wants to know. Okay.
Oh shoot, I'm not looking at the ELE202 chat. Yeah, I'm using the 6th edition. Yeah, so I'll post this PDF up online as well with just some annotations. So these two, yeah. What did I write here? Yeah, 11v1. So these two are the same.
There's practice problems posted for each chapter, so like you don't even need to use the textbook to be fair.
Oh yeah, for sure. Well, I think the practice problems reference the textbook. No,
Yeah,
I
mine.
forget. Yeah, but yeah, the major problem I have with the textbook is that they don't explain very well. They don't explain very well how to solve them. They just sort of post the numbers and expect you to figure out how it goes in between. So
I thought
yeah.
the textbook. I heard the textbook was like good to learn from. I don't know.
I didn't
guess
find.
not.
You can find it. Obviously, every single person is different. Every single person learns
Yeah,
different.
that's true.
I've found it's better to learn off the YouTube, off of YouTube. I posted a
Yeah.
link to the playlist in chat. I'll post in the description for people watching the recording. I found it's better to watch someone else doing it and then apply it to
Yeah.
the textbook. If you find textbook better, yeah, definitely go for it. But you need to find what's best for you. So yeah, I'll
To be
post.
fair, like I feel like this, like after the midterm is just like is mostly same stuff, but it's just like a couple elementary steps.
Yeah, I know.
But like yeah, I guess that's why they gave us like 3 hours for our
Yeah, for
questions, 'cause
sure.
it's taking a lot.
So yeah, these are simpler questions. You need to go through the textbook, find the harder ones, really note down in your head like the techniques, because ultimately, harder circuits, easier circuits, they use the exact same techniques.
Yeah.
All right, so I think that's all for now. Is there any other questions? All right, that's good. You better not have any extra questions. All right.
Hopefully, I got it.
So, thank you all for thank you very much for attending as well. Because I'm glad. I really hope you guys find it more useful. I hope you guys use this to solve your AC, especially if you still have the if you have the tutorial tomorrow or Thursday. So, thank you all. I think that's it. Let me stop the recording here.